Good morning again. So today our first speaker is Mr. Ibrahim Kronfol. He's a project manager, senior mechanical engineer, a sustainability and value engineering auditor with over 15 years of experience at Dar al-Handasa, Share and Partners. He has a successful career record and extensive design and management experience of major projects in the Gulf and the Middle East. So with the firm since 2005, Ibrahim has been working on a wide range of sustainability, building services, infrastructure, energy, water, and project management sectors. He has contributed to a range of diverse applications within the construction industry. He also has provided sustainable engineering design solutions for various design aspects, including airports, hotels, medical centers, hospitals. Ibrahim has developed a comprehensive understanding supported by academic certifications of project management procedures, value engineering practices, and green buildings design throughout his career experience. So Ibrahim, the floor is yours.
Good morning, ladies and gentlemen. Some of the colleagues asked me about what I will be speaking. They didn't get the title. I promised it will be something interesting. Hope this dual core hot well approach will meet their expectations. We'll be covering during this session the challenges facing the HVAC industry for the built environment, the dual core hot well approach, and I have split this into three parts: the equipment shaft, the hot well, and what we find out of this from the building synergies. And then I'll go through a case study and we'll see the benefits out of this approach. And, everybody knows that we have a climate action commitment and the world is pledging towards net zero. And the HVAC industry, who is responsible for 40% of the global emissions, have a lot to do. The action is required from the main three stakeholders: the manufacturers, who are responsible or they need to work on improving the efficiency of the equipment, the building designers and the contractors as well. They need to play a role in fitting in efficient HVAC systems through optimized design integration process, and the end users or operators, they need to work on enhancing their efficient manner in operating the buildings and the systems. To go back and focus on the type 2 or our second group of the stakeholders, the designers, we noticed that the majority of the global HVAC installations are DX units. And for those who do not know of these units, these are simply heat pumps. They reject the heat or they pump the heat outside the building. In order to these units to be installed in the building, these units need to be placed in a strip of the building facade and stacked vertically for high-rise buildings. And they assume that, the designers assume this portion of the area is a technical space, and they treat it and they forget about it mainly. This portion usually takes 5 to 12% of the building facades, which we are losing from the views. But the main issue, cause of concern, is not the facade, it's the stack effect. Hot air rising will mix with heat rejects from upper level condensing unit, causing higher concentration heat and considerable temperature gradient. As you see in this picture, that the condensing units rejecting hot air will be blowing the air up. The gradient will be going or rising up throughout the building. The suction at the higher levels will be taking the hot air, and this will cause for derating of the condensing units at the higher levels. But in order to assess this, I have looked into key performance indicators, and these are three: the system performance, the building aesthetics, and the commercial perspective. From the building performance, the heat reject re-entrainment, we see that it's a reduced performance for the condensing units. And the second, the aesthetics, we have also lost part of the building, and the architects needs to deal with this strip. And for the views, the commercial perspective, this portion that we lost is a prime sellable space, and this will add for the selling or the commercial feasibility of the projects, and the high performance cost of the running cost due to the derating of the equipment. Our main focus was to work on these three KPIs. And we find in the market that there are some approach to or attempts to solve this recirculating issue. This is an approach that was proposed by one of the manufacturers to use to separate the intake from the discharge. But going back to the KPIs, we see that only the performance have some improvement, but we have lost more area on the facade. The views, we have lost more area, and still we didn't, we're in the commercial perspective, we didn't solve it. Like, this is the introduction to go to the dual core hot well approach. And my main focus was to split between the hot and to separate the units from the heat reject of the condensing units. The design philosophy here is to create a vertical dual core through the center of the building. As you see, I thought to keep the full periphery of the building clean and without keep it to the architects, and to center our focus within the core of the building. And I've created two main cores in the building. One, I call it equipment shaft, where we'll be housing the equipments. And the second will be the hot well. Also, we refer to this as the hot aisle. We refer to the equipment shaft sometimes as cold aisle and hot aisle, similar to that used in the data centers. The equipment shaft is a vertical shaft with gratings on each floor level, designed to allow the air to circulate and provide the required make-up air to the equipment, such as these as you see there. The air at the equipment shaft will be supplied from the bottom and from the top of the shaft, and we will need the equipment, these condensing units will be pushing the air towards the hot well, forced towards the hot well. The make-up air will be fully ambient within the equipment shaft. For the hot well, or the hot core, it is actually a heat pump, a heat dump, vertical shaft running vertically and parallel to the equipment shaft. The hot well plays the main role of routing the heat rejects through and towards the specific location, and could be routed towards a recovery. We have collected all the heat rejects towards a specific points that we can choose at the technical floor, bottom or the roof, and there's an opportunity to use this for recovery. We have also, we need in this approach to use backdraft dampers on each termination to prevent re-entrainment of the air towards the other condensing units. And we need to insulate both shafts to prevent heat gain back to the building. And these were my first approach, but we find some extra 3 bonus or building synergies out of this. The first bonus point was the passive parking ventilation mode. As you see, the equipment shaft is open to the basement, parking from the bottom. The bottom is permitting make-up air of all running condensing units to pass through the basement and the parking floor. This have created or catered for the parking ventilation. The second bonus point is an opportunity to discharge all the exhaust fans or recovery that are mainly at lower temperatures, close to the indoor conditions, to that equipment shaft. This will help in tempering the make-up air intake to the equipments and will enhance the performance. Third bonus is an opportunity or alternative use to place packaged rooftop units or air-cooled chillers within the building. But this needs further validation and study. Going back to the KPIs, we see that on the performance aspect, the condensing units have an optimal performance, and we benefit from the passive parking ventilation. We have improved on this. The building aesthetics, we have no impact and no constraints on the building aesthetics, no limitations for the architects to work on this. And for the commercial perspective, we have full exterior views. Also, we have saved on the operational cost that we were suffering from on the derating of the condensing units. And there was also a hidden commercial gain that the full parking ventilation fans were saved, and we can save on the full parking ventilation fans, and we will take a case study and run again through how we size the shafts and how to quantify more the benefits of the dual core hot well approach. And I took a case study, a building, an office building in Dubai, 20,000 square meter built up area. It has a basement of 4,000 meters squared and a ground floor, 15-story building, 1,000 meters squared, typical floor. And we placed a dual core shaft within the building core near the elevator and the stairs, as you see there. And we insulated these cores. We went through 4 steps in sizing the dual core. First, step 1 is to estimate the cooling load and select the condensing units. This was a VRF system. The floor is estimated to for 36 tons of refrigeration cooling. So we selected 22 tons of VRF condensing units and went to step 2, and we extracted the airflow of the condensing units. It was 7,100 LPS of heat reject airflow per condensing units. Step 3, we added the airflow and applied a diversity factor, and we reached 138,000 LPS to be that will be discharged to the hot well. Step 4, we worked on sizing now the dual core. We looked at the equipment shaft. We took the 138,000 and we sized it as the first run on 12 meters per second. Then we added the equipment footprint, because we have equipment footprint that is blocking the flow. We added 2 square meters, and we reached a 5 meters by 3 meters equipment shaft. And we assumed that the hot well is of the same size because the air is flowing there, and the full hot well dual core are 5 meters by 6 meters, which is almost 3% of the floor built up area. To confirm these estimates or these calculations, we run a CFD analysis or CFD model. The CFD model simulation is used to optimize the multiple parameters, mainly to size the shaft or to confirm the size of the shaft, the location of the pressure relief within the shaft, the height of the shaft above the building, because we were worried of the discharge or how stack is above the building, and the size of the openings within the hot and the cold aisles. The achieved results indicate that the pressure effect resulting from the wind flow above the building can be used to assist in the buoyancy effect, as you see in the velocity contours. These clearly show a very active flow pattern is achieved within the shaft, whereas all the hot air is discharged at higher level. We have generated 3 contours: the velocity, the pressure, and the temperature. And we were worried about the pressure more than the velocity. The pressure, because the condensing units have a limited static pressure, we cannot exceed. We were stuck between not to exceed 60 Pascal this static pressure or pressure loss of the full system. As you see at the pressure contours, that the pressure at the cold aisle is the lowest, indicating the ambient air into the shaft, and the pressure at the hot aisle is the highest, showing that the air is pushed to the environment. And the reported pressure differential between the cold and the hot aisle is 60 Pascal, which will not affect the operational condensing fans, and will deliver smooth, will be acting, will have no problem for the fans of the condensing units. The temperature contours, as you see, that the ambient conditions is achieved within the equipment shaft, and this was the main focus of this approach. And we have no re-entrainment of air whatsoever throughout the all equipment at full levels. And what are the benefits of this approach? The first purpose we achieved it is the enhanced efficiency and operational savings. We have worked on stopping the derating and maintaining that the equipment are operating as per the design conditions. We have a capital and operational cost savings we saved from this example, from this case study, 31,000 LPS of the exhaust fans. We can omit them. And this is a significant return on the capital and operational cost of the project. We have also end-of-life equipment replacement cost savings. The equipment now are located within the protected shaft. It's away from the extreme weather conditions, sun, rain, snow, and wind, which we expect to extend their expected lifetime. We have also potential energy recovery. The heat is all streamlined in one shaft, and we can gain from utilizing this heat in preheating hot water or for other heat recovery applications. Also, we gained on the aesthetic improvement. The centralized shaft has provided the building with full views now, and there is no limitations. Operational and maintenance benefits. The maintenance can have more easier accessibility to the equipment and with more safe environment. This is what I have. I can conclude that, or to sum up, this approach have worked on the short-circuiting phenomena. That's a common HVAC problem in the high-rise building. The dual-core hot well approach is an integrative design methodology. We need the mechanical engineers and the architects to work together to achieve this approach. And it's proposed to manage heat gradient flow and to solve the short-circuiting phenomena while adding synergies as the passive parking ventilation, enhanced building facade and aesthetic daylight perspective, optimize equipment performance, and extend the equipment lifetime. Thank you.
Thank you, Ibrahim, for this interesting presentation. We have now 2 or 3 questions maximum. So,
thank you. Thank you, Ibrahim, for the presentation. It's quite interesting, actually. The idea of the condensing unit, I totally agree with this. We already did this like 7 or 8 years ago in Kfuri building Demco, Nantes, if you know. I was with a contracting company back then, and it was VRF units. But we did louvers, and we did CFD calculation, and it's working just fine. The performance of the units is quite good until today. And one side of your technical presentation that I'm not seeing here, which is the capex of this shaft. I didn't see the, let's say, which, is it ducting? Is it galvanized? Is it concrete? What kind of, what's the material of this shaft?
These dual core are shafts, concrete shafts. And
So you're using concrete?
I am using a typical or a classical shaft.
Because you have additional
But
costs.
we are adding insulation for both shafts just
Exactly.
to
But Ibrahim, this insulation should be fire rated because you're taking the exhaust from the parking, right?
We did not yet went to an actual project for this. It's just a conceptual idea that we have developed it and presented with a CFD to ensure that it's working. Back to your first question, it depends on the height of the building. We've read multiple studies on this problem. As you go up, the heat will accumulate and there will be a temperature gradient. But you see that we've done multiple projects, enhancements on such case in Dar al-Handasa to prevent this.
And I agree with you, but again, it was like G+26, Kfouri building, and we did CFD back then, and we didn't need any additional shaft for the outlet or exhaust of the condensing units. So again, the idea is very good, but the capex or let's say the initial cost for this would be quite high for such a building. And of course, if you're thinking about exhaust from the parking, you definitely need fire-rated insulation, calcium silicate insulation, which would be very high.
You saved on the parking ventilation.
I mean, I didn't really see any benefit for the parking ventilation because you still need active exhaust. You still need fans over there, exhaust fans.
Need maybe jet fans to circulate, but the main 31,000 LPS for this example, we've saved on this, the fans and the operational cost of that.
Basically, once you put jet fans, you don't really need ducting and the exhaust fan. Okay.
Is there any other questions?
Thank you.
We can accommodate for one more question. At the back, Short and concise, please.
Okay. Thank you for your interesting lecture. I want to just to give a point about some serious matter. If in case happen fire in the parking, the smoke will come in 400 degrees Celsius and will come through that hot ice shaft. So all the smoke will come into the flat because all the opening from the flat to the wheel for extract, this must be fire rated because if it's not fire rated, all the smoke will come inside the flat and will create a huge problem for fire safety.
I've heard with some discussions with colleagues about what we will do during fire.
Yes.
This will be further studied when we get a project that we will be implementing. But as a first response, we're thinking of closing this shaft and to work on another means to extract the smoke and to deal with the fire. But we did not yet have a full project case study that I can talk about. It's just like a conceptual idea that I'm presenting here.
Last question.
Thank you, Mr. Kronfol. Since this is an ongoing research study, I don't mind at all with the questions and the debate you're having. But one thing maybe you have to add to, which is noise that can be reaching the apartment itself, and the access panel. Access panel, I believe it should be on the stairwell, not inside the apartment, for many reasons. First, the type of the access panel, access of the technicians going into the stairwell rather than going into the power. So please include in your following steps here ideas of noise, accessibility, and then you solve the problem of the smoke as discussed.
Thank you, everyone. Now we'll move on to